I'm now going to present the sub-sentence level experiments that we performed in the confidence estimation group. To give you an overview of the talk, first I want to motivate the approach and then describe the word level features that we used. There's a couple of words about the word error measures that we use for tagging words as correct or incorrect, because we have a bunch of different possibilities there. Then I'm going to present some experimental results and give an outlook. So first of all, the motivation. If we want to do sentence level confidence estimation, we have the problem that the sentence as a whole might be incorrect, but it might still contain some correct parts. So we want to be able to identify those correct parts, even if the sentence as a whole is not correct. And we performed a small human evaluation exercise that Alex is going to talk about later. And there only 30% of the translations were rated B, 4 or 5. Well, we had an error scale from 1 to 5, and 5 was top. And only 30% were rated acceptable by the users. This classification of correct or incorrect is much easier on the sub-sentence level. And what we hope as well, that if we have confidence estimates for the sub-sentence level, they might allow for a recombination of different translation alternatives, as George mentioned before already. So the possible applications we see for sub-sentence level confidence would, for example, be highlight incorrect words or parts of the sentence for post-editing, or if we are in interactive translation environment, for example, we want to output only those words that have a high confidence and just discard the others, or the recombination I mentioned before. So for the word level features that we came up with, the features that are marked here with a star are going to be explained in more detail later on. So first of all, we have the identification of incorrect parentheses and quotation marks in the sentence. So those were simply labeled in the output. We have average of semantic similarity for the words, the wordnet polysemy count, and the wordnet polysemy count with regard to a tag corpus. Those are the semantic features we had. The next three are relatively similar. They just distinguish whether a word occurs in any target sentence position, and then determines the relative frequency of all hypotheses in the embed list containing this word in some position in the sentence. We do the same summation, but instead of determining the relative frequency, we take the normalized rank sum or the word posterior probabilities, but I'm going to explain them later. And we did the same thing for the exact target position. So the difference is here we regard all sentences containing this word somewhere, and these are only the sentences containing the word exactly in that position. What I did here is to classify as well whether those features are dependent on the base model that we used or not. So we see most of them do not depend on the base model, but the average semantic similarity? Yeah, sure, thank you. Depends on the base model because it makes use of the alignments, and those down here make use of the base model because they actually take the sentence probability. Then we have some more features that depend on the source and the target language as well. This is the model 1 that Erin already talked about and that the MT group used as well. This is not model dependent. And here are some features that depend heavily on the statistical machine translation model that we work with, which are those three that are better implemented and that rely on the alignment of the words. And the last two are the index of the alignment template that contains this word in the translation, or simply a marker saying whether this word was translated using a rule-based system or the actual statistical system, because the system had a part that did rule-based translation of data expressions, numbers, etc. So this is just a marker for those two. So to say a bit more about the semantic features, the first one was the average semantic similarity. So if we want to compare two words and determine their semantic similarity, we compute the weighted sum of n-gram overlaps in the word-net glosses of the words and words related as well. So if you look at the tree or hierarchy in WordNet, this computes the overlaps not only for those two words, but for other words contained in the subtree as well. And then the average similarity between the words and other words aligned with the same source word in the top ranking 3 hypothesis was computed. And this was implemented by John, and it was an algorithm by Banerjee and Patterson, who adapted an algorithm from LESS that was based on conventional dictionaries, and they adapted it to WordNet. The second semantic feature we had was the WordNet polysemy count, that is the number of senses stored in WordNet. And the third one is a variant of this, which counts the senses, but only those ones that appear in the tagged WordNet corpus. And okay, we had a couple of features that were conceptually quite similar, that were word posterior probabilities and the relative frequency and rank sum. So what happens there is that for the word posterior probability, we sum up the sentence probabilities for all the sentences in the invest list that match somehow, like we define a set of matching sentences, and what that is going to be explained in the next slide, because we have 3 different variants of those matching sentences, and then we just normalize it over the whole invest list. And the relative frequency is the same. It finds all matching sentences and then simply counts them and determines the relative frequency. Here, n is the length of the invest list. And the rank sum does not only count sentences, but instead it always sums the ranks of the sentences. And this is motivated by the idea that we want sentences that appear near to the top of the list to score better than sentences that are below at the bottom of the list, because we think that they might be better translations, so we want them to score better, and then we normalize this as well. So to say what the matching sentences are, like the ones that we're going to compute the sum over, we had 3 different variants that actually made it into our models. The first one is simply checking whether this word E that we're looking at occurs at exactly this target position that we saw in the hypothesis, and taking all the other translation alternatives into account where this word occurs exactly in the same position. So this is a very strict measure of finding matching sentences. The second one down here is less strict. This compares the set of source positions that is aligned to this target word. So every time we see this target word as a translation of the same source word, we will count. And this is more flexible because the target position might change within the sentence due to reordering or insertions and deletions. And so this is a more general measure. And then the less strict measure is the last one, that simply accounts whether the word occurs in the sentence or not. So we sum up over all sentences that contain this word anywhere within the sentence. And the fourth probability, which unfortunately did not make it into the data, but is under construction, is checking whether the word occurs in a position that is Levenshtein aligned between the hypotheses. Okay, so now to explain the word error measures that we used for tagging a word as either correct or incorrect. We implemented a couple of different variants. I ordered them by strictness. So the first one here is a very optimistic measure. It always counts a word as correct if it occurs in any of the references. So if we have seen it somewhere in one of the references, this word will be labeled as correct. The second one is the word error rate, which is well known from speech recognition. We will count the word as correct if it is Lebensstein aligned to itself in one of the references. Then the position independent word error rate checks whether a word occurs in the reference. And this is a bag of words approach. That is, we also take the number of times a word occurs in the references into account. And the next measure is less strict. This simply takes the set of words without regarding the number of times a word occurs. And then we also implemented some measure that is a bit different from the others, where we checked whether this n-gram, that is the word and its predecessors, occurred in the references. And for all of those four, there are actually two different versions for extending them from one reference to several references. We can either pool all the references we have, or we can only compare our hypothesis to the nearest reference that we have got. So pooling would mean for the word error, for example, we will always label a word as correct if it's Lebensstein aligned to itself in one of the references. And in the second variant, it will only be counted as correct if it's Lebensstein aligned to itself in the nearest reference. That is the one that has the least distance in edit operations. Okay, so one slide about the experimental setup. For the word level features, we worked with a set of 700 source sentences, roughly 300 source sentences for the developed set, and the same test set as for the sentence level. And we took the 1000 best lists, so the number of target sentences is given here, which yields around 20 million running words in the training corpus, 7.5 million running words in the developed corpus, and 26 million words in the test corpus. And to show you how the error measures label the words in those corpora, we see here that this is what I give here is the percentage of correct words in the corpora according to the different measures. So we see that the first one is very strict. It only labels a very small percentage of the words as correct, and the other ones get less and less strict. So this is a very optimistic measure. It will say like around 80% of my words are correct in the corpus. And the ones that are marked in blue here are the ones we actually tested, which I'm going to present results on. We tested all of them, but the results are given for those. So first of all, we investigated single features using a naive Bayes model that Alberto implemented, and that was used for the sentence level as well. And the error measure we are looking at here is the position independent error rate with respect to the nearest reference in our reference set. And the performance measures I'm giving here is the A-ROC, that is the area under the ROC curve. We saw that before on the sentence level. And the CER is the classification error rate. So it counts all words that have been labeled as correct but are incorrect, and vice versa. So every word that is tagged wrongly. And the baseline in CER is simply computed by tagging every word as correct. So we get, if we assume everything is correct, we get an error rate of 36%. And the features I picked here are the ones that did best in those experiments. So we see that those three different variants with the word posterior probability, the rank sum, and the relative frequency that take any target position into account actually performed best. We get an error rate of 30.8 to 30.9% for those 3 different variants. And here the AROC is 41 point something. And then the next best feature was model 1 in our case, which is only slightly worse. And then we get the word posterior probabilities, rank sum, relative frequency with regard to the aligned source positions. And the same with respect to the fixed target positions. So this set of features seems to work quite well. And here we have the alignment template identity. That is just the alignment template containing that word. And what we see here, which is very nice, if we combine all the features that we have got, we had 17 in total. If we combine all of them using the naive Bayes model, we get down to 29.6 classification error rate and 47.2 in AROC, which is a nice improvement over the baseline that we got. Okay, for the CR we have this baseline, and if we assume only the single best feature, we still see that we can significantly improve that. If we go to the combination down here, we get a larger AROC value and a lower classification error rate. So comparing now the naive Bayes model to the neural net that we trained as well. Here we trained a neural net with 20 hidden units because this gave us the best error on the validation set, so we picked that for testing. And these are the error measures that we trained on. So we see if we train with respect to the word error rate, we get an AROC of around 37 if we combine simply the best 3 features, which can still be improved if we combine all features, and which gets even better if we combine them using the neural net instead of the naive Bayes model. And this is consistent with all the 3 error measures. Like here we see as well, if we combine 3 of them, this is significantly better than the performance of the single features, and gets still better if we combine all, and then if we go to a more complex architecture. So we also see the same behavior if we plot the ROC curve. This is the ROC curve for the position-independent error rate. So what we plot here is correct rejection against correct acceptance. And this down here is the performance of the single best feature using the naive Bayes model. And we see that if we use the top 3 models, we get something that improves on this. And the combination of all the features using the naive Bayes is pretty similar to the top 3 features, but we still get better if we use the MLP with 20 units to train the whole thing. So that were the results for the sub-sentence level. Now the question is how we're going to apply them. And we have some ideas that we want to explore after the workshop. So the idea is to use a search criterion that is based on this confidence estimation for the words or for the sub-sentence level. And then we can try to recombine different translation alternatives and get hopefully a better translation out of those. But there are a couple of problems with this approach. Like, for example, the sentence length has to be determined somehow. And if we only look at the confidence estimation, like as probabilities, for example, like posterior probability or something, it'll tend to prefer shorter hypotheses, of course, because we multiply a lot of small probabilities, and so it will always tend to prefer shorter hypotheses. So one solution to this might be to normalize by the sentence length. But then we also have the problem of a criterion for selection of the target words. Like if we pick the best target word for each target position, we have the problem that we can have inconsistencies, because the same word might pop up in different positions because it might always have the best confidence in this position. And a way to overcome this might be to represent the search space in a word graph, because there we can implicitly encode only valid paths, so we won't run into that problem. Okay, so an outlook, apart from the recombination that I explained, we still have more features to try because we started the work on the word level confidence estimation rather late in the workshop, so we still have some features that are there but didn't make it into the data, so we still plan on testing them, and that was it for the subsentence level. So I'm going to pass over to Alex to talk about the MT evaluation.
All right. So this is where we solve the problem of MT evaluation. So this is sort of a side project in the sense that we conducted a small experiment collecting human evaluation data and then tried to correlate some common error measures with that. In some sense, it was sort of tangential to what we did because it wasn't directly involved in our task. But on the other hand, this issue is sort of central to everything machine translation, and in particular for us because we need to choose some kind of error metric to estimate. So this is why we did this. So we've heard all these things all day. Clearly, there's automatic evaluation is useful because human beings are so inexpensive. A lot of the metrics that have been proposed, there have been demonstrated correlations with human judgments, but they've typically been at the document text corpus level, whereas we really require sentence level evaluations, and that would be in bold, I could say. So the question is, how would we pick such a metric from the ones available, or how might you design such a metric? And basically what we decided for our task is that the score, we would like the score to reflect the level of adequacy for a particular application. And the way that we estimate whether or not a metric predicts this is by correlating with human judgments of task adequacy, which we, for now, assume to be our sort of best measure of such things. So very simply, an error measure takes a hypothesis and references and potentially uses other data from the world and produces scores. So I'm going to go through quickly the ones that we considered, and by now I think they're pretty familiar to everyone. But, one thing I should say is that so far in the presentation we've kind of talked about word error rate, and sometimes you've seen word error rate G. We've always pretty much been referring to word error rate G. So regular word error rate is just Levenshtein distance normalized by the length of the reference, with which it has minimum distance. And word error rate G is normalized by the length of the alignment. And you'll see in the correlations there's actually a difference here. So we always use word error rate G. Position independent error rate just treats things as unordered, so it doesn't penalize sort of movement of words. And again, normalized by reference length. So these are the ones you've seen a lot of. So blue is this geometric mean of n-gram precisions. It has a length penalty. I should point out these two things. So the MTT mentioned this, but smoothing the precisions can be useful because the geometric mean is very harsh if you get a 0. So you can smooth them in the obvious way. And what we also did was to adjust this length penalty. And in the same way, we adjusted it to be sort of less harsh, sort of the intuition being that on a sentence level, you kind of get much more variability that would sort of, average out over the course of the document. But we found that the standard length penalty was too harsh, and then we got better correlation adjusting it. We also have NIST, which is related to blue, but is an arithmetic mean of n-gram precisions, and also weights these n-grams by their sort of information weight, which is basically just the less common ones get higher weight. Finally, we looked at the F measure, which is intended to be sort of a more standard or more intuitive way of looking at MT errors. So this is the way it's defined. So the F measure is just the usual F measure, the harmonic mean of precision and recall. But the interesting part is the way in which we define the size of the match between a hypothesis and a reference. So it's the maximum of this expression, which is basically some sort of averaging over the length of these runs, non-conflicting runs of words. So Let me show you this picture. So I stole this from Milan's paper. But basically, if you have a hypothesis, and these are words in the hypothesis, you have a reference, you can draw dots in all the places where they match. And then you want to sort of enclose these runs by boxes in such a way that none of the boxes overlap in any rows or columns. And so this is a run of 4, a run of 2, a run of 1. And then you sum them using this formula. So in theory, k is a parameter. Originally, it was proposed to be 2. So this would reward runs more than, so that a run would be worth more than single matches, an identical number of single matches. But apparently later work correlated this and found that k equals 1 is sort of as good as anything, which is at that point not terribly different from just sort of a position-independent error rate, because you're basically treating these as bags of words and you're just seeing how they match. So we'll see in the correlations that kind of shows up. And we didn't do any testing with different k's, but it would be an interesting thing to look at. So this is the process by which we actually collected our data. We had a live server client system. We had a big database of sentences, and we distributed them such that we maximize the number to get 2 votes. And the idea behind having this sort of live system is twofold. One, it's convenient for users because they can do as much or as little as they like, sort of whenever they want, and we don't have to give them a big list that's really intimidating and say, here, do this and get it back with. And similarly, we get their data immediately, so we can start processing as it comes in. So I don't know if you can read this, but this is just sort of a sample screen of what the client sees, and they see a hypothesis, they see a reference, and they're asked to rate the hypothesis against the reference on a scale from 1 to 5, which I'll cover shortly. So this is what they saw, and by placing the hypothesis first, we tried to encourage people to read the hypothesis with the reference, although obviously we had no actual control over that in this setup. So we asked people to rate sentences in this fashion, 1 to 5, and we gave them, so all the non-bold text was visible to the user, and these are sort of task adequacy descriptions that I'm going to talk about just to sort of justify these levels. We also gave an example sentence and kind of how that could be mutated in a sort of obvious way to produce these scores. So I'm going to go over this. So a 1 is basically considered useless, captures no meaning. It might be a perfectly fluent sentence, but if it doesn't capture the meaning of the reference, then it's considered a 1. So it's just highly adequacy bias. And at that point, there's no task that's really useful. A level 2 is considered poor, but it might have some keywords. So it might have some extra random words like banana, but it does have dog and walk. So you might be able to use such thing in a cross-language IR setting, something like this. A 3 is sort of maybe Babelfish level. It has some amount of meaning, but typically there are serious errors that might hinder comprehension. But at least you could get some gisting. It might be useful to sort of, as a human being, maybe pick documents that would be interesting to get professionally translated, things like this. 4 is considered pretty acceptable, captures most of the meaning. Bob walked the dog, so there's a slight grammatical problem, but all of the basic information is there. And at this point, you could ask a human to post-process, post-edit this, and get good output. And finally, 5 is just sort of brain. And the example, of course, is tailored to show you that it doesn't have to be identical to the reference to be perfect. So we ran this system during the course of the workshop. We asked and begged people to use it, and we were able to give it to 29 people to waste some time. We got about 20 user hours logged, so people spent an average of a little under an hour, about 40 minutes. Total of 705 sentences were scored by 2 users. 72 of them were calibration sentences were put in there just to see if people were willing to get 1s and willing to get 5. And so we ended up with 633 hypotheses scored. And we had a scoring rate, we calculated it was about 74 sentences per hour, which just suggests that this data can be acquired at sort of a reasonable rate. It doesn't take people. It's not a fast. For anybody who's done it, as they know, it's not a really quick thing to do, but it does move reasonably quickly. So one more stage before we get to the correlations. Despite these sort of guidelines that we give, voters obviously are going to differ in their perception of what's a 3, what's a 4. So here, these are actual just histograms of the vote counts for 2 separate users. And as you can see, there's a pretty significant shift here. In fact, you could almost take voter E and then shift all the votes down by 1 and get a comparable rating. So to compensate for this effect, we sort of basically converted the scores to these approximate percentiles, and this idea is characteristic idea. So this is how we did it. We take the histogram, and we basically plot this light blue line, which is just sort of an approximate cumulative distribution. And then we take a 3, converts to a 0.7 in this case. So I think this is fairly clear. And as you can see, the computer kind of like improvised a new layout for this slide, but you kind of get the idea. So as you can see, the 3 for voter E is around 0.3, whereas a 3 for voter F is around 0.7. So it's taking into account these discrepancies. I should also mention that when we calculate the average human score, we weight these percentiles with the total number of hypotheses scored by that user. So it's sort of a reliability judgment. If we have more votes from this person, we're more confident that the percentile is accurate. So to summarize the data we gathered, first of all, standardization did increase the correlation from 0.43 to 0.46. And before y'all say that's really low correlation, wait till you see the other ones. The confusion matrix, certainly there's correlation going on. It's not terribly tight, but we'll see. And this is the distribution that we saw for those. And I should point out that these 1, 2, 3, 4, 5 don't really mean literally votes 1, 2, 3, 4, and 5 anymore because we've standardized everything, so it's on this continuous scale. So we've basically rebinned all the scores, all the continuous scores, this includes human scores, NIST, blue, etc., into bins with equal proportion to the original distribution of votes. So this is the same distribution you see in the original raw votes, but it's also the same distribution that you see whenever you look at any of the error metrics broken into these bins. So finally, correlations. These are correlated against the first human annotator, which is just quite literally the first person to rate a sentence, so it's an arbitrary selection of one of the 2 human voters. So you see here that the second human correlates more highly with the first human than any of these error measures by a significant amount. Within the error measures, you see word G and NIST having maybe a slightly higher correlation than the others. This result is more or less why we selected these 2, but it's not clear, particularly when you add these, that there's really a significant difference at this point. But nevertheless, we can be fairly confident that human-to-human correlation is higher than these error metrics, which suggests there's some room for improvement at the very least. And probably position-independent error rate and the F measure, which, as I mentioned, is with k equal to 1, approximately the same as position-independent error rate, seem to show perhaps significantly less correlation. So clearly all these error bars overlap, but we can sort of draw some approximate judgments.
Error bars are 95%.
Yeah. The other thing to point out is that we have 633, n equals 633, so if we were to collect more data, we could hopefully kind of shrink these error bars a little bit. This is the same plot, but in the back I've plotted here the correlation of each error measure with the human average. So in a sense, it's not really fair to compare these to this column because this human being only is being correlated against a single human, whereas these are correlated against averages. But it does demonstrate that there is a lot of noise in the human data, and that by averaging the human responses, we do get higher correlations with error measures. Which also suggests that it might be worthwhile to gather more than 2 votes per sentence. And finally, I just wanted to show you one scatter plot. So first of all, these are the raw data points, the human average versus NIST. And these big blue dots you see are the averages of these 5 bins that I talked about. So the idea is that if you average essentially over large numbers of sentences, you do get this actually, very reasonable correlation. And this is the effect that has been reported on, that NIST and blue correlate well with human judgments. They do if you take averages over large numbers of sentences over a document over time. But effectively what we've seen is that for sentence level, they really don't. and this is a problem, and this is what we've heard all day, to reiterate that. So I think I've mentioned these things. It would be useful to collect, get more sentences scored and try to shrink the error bars and find out what differences are significant, if any. And gather more votes per sentence to hopefully reduce the noise and see how high the correlation actually goes. But of course, the conclusion is we need better metrics at the sentence level. So.
I'll be brief. So just to summarize our results from the workshop, we've done basically 3 big experiments. Sentence level confidence estimation. The main findings were that adding an extra machine learning layer improves discriminability results over just what raw statistics that you can get from the base model. And unfortunately, we didn't get any significant improvement on the 2 applications that we tried, model combination and renaming. At the sub-sentence level, we found the same thing as up here, that when we add machine learning layer, it improves discriminability. These results seem to be somewhat more promising than the sentence level, in that use of more sophisticated machine learning techniques helped more, and actually the results, if you look at them in terms of AROC, are slightly better than the ones at the sentence level. And we also found here that that using richer feature sets helps more. So the sub-sentence level problem seems to be a little more tractable, more clearly defined, which is understandable because you don't have this sort of fuzzy match that you're using at the sentence level. In our human trials, as Alex just mentioned, we didn't really find any significant difference between all the measures that we tried at the sentence level. And we used 2 that happened to be higher, but we wouldn't want to argue that they're really significantly better. And we also found that at the sentence level, the inter-annotator agreement is very low, but it's distinguishable from the other measures. So, to conclude the workshop, we're not at the stage yet where we can honestly claim that confidence estimation for machine translation is useful in an application. And basically, we think that's because we need better solutions to the 2 basic problems that I mentioned at the beginning. To say, yet again, better evaluation metrics at the sentence level. And another thing that would really help would be better MT output, because as translations get better, the problem of picking incorrect versus correct becomes more clearly defined. So, 2 of the most promising future directions that we want to try are using the existing measures, perhaps with some extra features, try some kind of filtering application. Can we distinguish between translations that are useful for IR and translations that are useful for kissing, for instance? And I guess the most interesting idea is, can we make some use of these interesting sub-sentence confidence estimates to do some sort of search or recombination? And that concludes.
Several minutes for discussion. The sub-sentence level confidence estimation, you reported sort of average numbers, right? So this is over all words. Is there a trend for some words that tend to be problematic as opposed to others?
I'll refer that one to Nicola.
Okay, unfortunately we haven't had time yet to look into that because, as I said, those results were very hot from the press because we started those activities rather late, so we didn't have time for a detailed analysis yet.
Yeah, so I mean, this is one of the things we hope to get at in the report, lots of these analyses.
Well, this can be in the neighbors model that we use. The neighbors model that we use for the spellings. This information is included in the priori probability of the word to be quoted. That is inside the model.
First, there is a priori probability of an English word being correct.
You can see it's live.
Don't think, can you say something about it and what kind of words are usually incorrect?
We can see it's live with.
Okay, you have a list. Another question?
Could you summarize again how when you did the multi-system combination, how you chose which output to take for which sentence? Which is the highest scoring one?
Well, yeah, so we kept, Simone's going to correct me if I say anything. We kept the two lists separate, right? So each system generated its own hypothesis, and then we ran confidence estimation layers separately on each and picked the one from each, over both lists, picked the one that had the highest probability according to its model, right? Yeah, so I think that's kind of a weak way of doing it actually, because you would like to ask each model about, you would like to basically merge the list and ask each model about the other's hypothesis as well. And there's some other possibilities that might improve the results.
Another possibility, of course, would be to try to learn the optimal combination, just feeding the Model 1 score, the Model 2 score, and the right choice to a classifier machine learning layer.
Because we don't want
The optimal combination. It's another way of
We don't want to admit that because that's not confidence estimation.
Yeah.
You're doing that, dispense with these
But
probabilities.
even if we would do this with the confidence scores instead of the base model scores, we would have better results. I don't know.
Okay, thank you.